What kind of trees do math teachers climb? We climb geometries. Get it? Geometries. So we are getting into the heart of geometry now, which is triangle congruence. And we had already discussed side, 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 and side, angle, side theorems, or postulates, really. And then I have angle, side, angle, 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 side, and hypotenuse, leg. So we're going to look and determine which of these will be proof enough or enough information to prove that two triangles are congruent. So first of all, I have angle, side, angle. Now, the important thing to know is that side, remember we learned in side, angle, side, the one in between needs to be included. So it needs to be right in between the two angles. It can't be separated. So you can see that AB here is the included side. It's touching both angles. It's not separated. And the question is, how many different triangles can you make? Well, I'm allowed to move this as long as I don't change the angle. If I tried to turn this a little bit, then I'm changing the angle. If I tried to turn this other one, I'm changing the angle. But these angles are specified, so I'm not supposed to change them. The only thing I can do is change the length of this side here. And you can probably see that where the two will meet is where those two lines intersect. And there's only one way to put together this triangle. And so when I record the lengths, I'm going to find out that AC is 9 and BC is 12. Again, there's only one triangle, only one set of values for the angles and the sides. Now, if I asked you to make AC larger, the only way I can do that is if I change one of these given values. And if I do that, then I'm changing the original 3. So as long as I stay with the original 3, then I will be okay for showing congruence. So again, if I wanted to make one of these larger, I have to change one of these 3. Even changing the side would make this side larger. So there's a relationship there between all of these sides and all of these angles. So the angle, side, angle postulate says if we give two different people a set of matching angles and a set of congruent included sides that have to go right between the angles, the triangles will always be congruent. So it looks something like this. If I know an angle's congruent, a side's congruent, and an angle's congruent, and the side is right between the two angles, then I know the two triangles are congruent. So in this example, I want to see which angle pair must be marked congruent to show congruence by angle, side, angle. And so first of all, I can see that this is congruent by the reflexive property of congruence. HI is congruent to HI. And then if I try to say, let me do this angle over here, because that looks nice, but the problem is that side is not between the two angles. So I don't want to use this angle. Instead, I'm going to use this angle and this angle. So if I show that angle FHI is congruent to angle GHI, then I have enough information to show the two triangles are congruent by angle, side, angle. So in reflection, why do we know we can make only one unique triangle given angle, side, angle? And hopefully you saw that when I set the two angles, that made the lines where they have to intersect. So there was only one place those two lines would intersect.